Welcome back. In this video, we're going to continue learning about liquids. We're going to discuss heat capacity, specific heat, and molar heat capacity. We're also going to learn about heating and cooling curves and evaluate how the temperature of a substance is affected by heat change. And then finally, we'll do some pretty heavy-duty calculations where we're going to calculate the total enthalpy change associated with various temperature and phase changes. So we first need to start talking about heat capacity. Heat capacity describes the heat that's required for any substance in order to raise the temperature of that substance by a degree Kelvin or a degree Celsius. Remember that the Kelvin scale is built similarly to the Celsius scale, so 1 unit Kelvin is the same as 1 unit Celsius. The specific heat capacity, sometimes just called specific heat, is the heat capacity per gram. So in other words, this is the heat that's required to raise 1 gram of sample by 1 degree Kelvin. And heat capacities are different for each substance within each phase. So if you take water, for example, it's going to have a specific heat that is different between solid, liquid, and gas. And that's a function of how the energy is stored in those molecules within each phase. For ice, we have a value of about 2 joules per gram per Kelvin. For water, it's about twice that, and steam is a little bit less than for ice. The molar heat capacity is very similar to the specific heat capacity. The only difference is that instead of it being the energy required to heat 1 gram of substance, it's the energy required to heat a mole of substance. When you take a look at the different values, we can see the only difference in units is moles. And in fact, if you were to take and apply the molar mass of water in this case, and multiply the specific heat by the molar mass, you would end up with the molar heat capacity. When you're solving problems and you need to determine which to use, specific heat or molar heat capacity, pay attention to the units, as that will tell you what you need to do. As I mentioned earlier, the heat capacity for a substance is different from all other substances. So a substance with a large heat capacity will require more heat in order to increase its temperature for a given amount. Water is very special in that it has the highest specific heat capacity for any other liquid. Metals, on the other hand, tend to have very low specific heat capacities. So therefore, that's why they heat up and cool off very rapidly. Because of water's high specific heat capacity, that's why you can leave a large amount of water outside in the hot sun and it's not going to heat up very much. That's because it takes a lot of energy to increase the temperature of a given mass of water. Calorimetry is a set of experimental methods that are used to measure heat that's given off or absorbed during chemical reactions. This could also be during physical reactions, meaning physical reactions, I'm talking about phase changes, whereas chemical reactions, we're talking about things like combustion or precipitation or a variety of other chemical changes. In both cases, however, we're looking at the transfer of heat. We can describe the transfer of heat in terms of the temperature change that is occurring. And again, we might use the molar heat capacity or the specific heat capacity, depending on the context. Q is the symbol for heat, as we've seen already, and this describes the heat either given off or absorbed as the temperature changes. We can use the sign of the temperature change to determine the sign of the heat. And remember, when we're talking about the change in temperature, the scale for Kelvin and Celsius is the same. So to prove this to ourselves, we can look at a change of 5 degrees centigrade, going from 5 degrees to 10 degrees. That's going to be a change of 5 degrees Celsius. If we look at those same temperatures, but in Kelvin, that would be 273.15 plus 10, or 283.15, and then 278.15. By taking the difference of those, we also get a difference of 5 degrees. So when we're taking the change in temperature, it doesn't actually matter if it's in terms of Kelvin or Celsius. It only matters if we're taking and using the actual absolute temperature, like we saw when dealing with gases. All right, we're going to try a problem here. So let's say that we have liquid nitrogen poured over a bowl of marshmallows. That will freeze them. If you put a marshmallow weighing about half of a gram into your mouth, how much heat does the marshmallow absorb when it goes from the boiling point of liquid nitrogen up to your body temperature? The specific heat of the marshmallows is given for you. So I'd like you to pause the video and try this on your own before I walk you through a solution. Welcome back. So because we're talking about changes in temperature, we need to use the equation from before. That is, that we can relate the change in temperature and the mass and specific heat of a substance to the amount of heat that is transferred. Now, what are we expecting to see here for the heat? We're expecting heat to go into the marshmallow. And so for the marshmallow, we're expecting to see a positive value. And that's because its temperature went up. So the change in temperature we can find by taking the difference between the final and initial states. And remember, because we're taking a change in temperature and the change between 1 degree Celsius is the same as 1 degree Kelvin, we don't need to convert to Kelvin. That means our total change in temperature is 233 degrees. So we can solve for the heat by taking and multiplying the specific heat of marshmallows times the mass times the change in temperature. That gets us approximately 230 joules. Let's now talk about what we call heating and cooling curves. So a heating curve is described here. A cooling curve is what we would see if we started at high temperature and went down to low. So you might think of it as taking this and rotating it around, so that way it goes the other direction. So what we're looking at is we're looking at the temperature change as a function of the heat that's given in. So for water, if we start with solid water with ice at -40 degrees, the first thing that we would do if we put heat into it is we're going to increase its temperature until it gets to its melting point. Once it gets to the melting point, we notice that there's no change in temperature, but instead all the energy is converted or used rather into converting the solid ice into liquid ice. Once we have melted all of our ice and now have liquid water, if we continue to add heat, the temperature will rise until we reach its boiling point. At that point, it will vaporize, and we will keep adding in heat until all of the liquid molecules are converted to gas. And after that, we can then increase the temperature. So what we notice is that there are distinct phases or regions, and it's a lot easier when solving problems involving heating curves to draw a heating curve, first of all, and then to break it down into chunks based upon the processes that are happening, whether it's a temperature change or whether it's a phase change. Let's talk about more about why we have the temperature changes and why we don't have temperature changes for the phase change. Before we move on, actually, let me describe this. So earlier when we looked at the temperature change, we related that to the amount of substance and the specific heat. We can also calculate the heat required to cause a phase change by using the enthalpy or heat of whatever that phase change is. So again, when we add heat to a substance, we can get two types of changes depending on what phase it's in. Within a given phase, the temperature will always increase when we add in heat. What's happening is that as we increase the temperature, the kinetic energy increases, as we learned from kinetic molecular theory. Temperature is directly related to kinetic energy, and the molecular motion increases. They move around faster. The molecular attractions are decreasing because the molecules are able to move around more, they're getting farther away from each other, and it's becoming more disordered. However, during a phase transition, the temperature is constant. Therefore, the average kinetic energy is constant, but the total energy is going up. So what we're doing is we're increasing the potential energy of our substance at that point. When we add heat in during a phase transition, our molecular attractions are going down as well as the order. So the molecules are less attracted to each other again, because now we're changing phases, going from solid to liquid or liquid to gas. There's more room in between the molecules, and therefore they're becoming disordered as well. Another thing that's important to recognize is that for any type of calorimetry, we're always exchanging heat between the system and the surroundings. And the heat that is absorbed by one was released by the other. So when we look at the system versus the surroundings, they have the same change in heat, but the signs are different from each other. All right, so here's an example problem. If we want to determine how much energy is needed to heat up 1 mole of ice from 40 degrees below zero to 130 degrees above zero, how do we do that? Well, we're going to need the specific heats and the heats of vaporization and fusion, because those are the processes that we're undergoing. The first step that I recommend you do is to draw out a heating curve. You can draw out a generic heating curve that shows the solid region increasing in temperature, melting, the liquid phase that is increasing in temperature, vaporization process, and then the gas phase that's increasing in temperature. When you know certain values, you should put those in. It is expected that you know the melting point of water being 0 degrees Celsius and that the boiling point of water is 100 degrees Celsius. And so we can somewhat arbitrarily put the other values of -40 and +130 somewhere in a relatively correct approximate location. We can now also divide up our heating curve into regions based upon the processes that are happening. And we have 5 different processes. We have a conversion within the solid region from low temperature to high temperature. We have the melting process. We have increase of temperature from 0 to 100 while it's a liquid, the vaporization process, and then the temperature change as a gas. And for each of these, we can quantify the amount of energy involved by using the relationship between the amount of substance and then either the specific heat and temperature change or the enthalpy of the process. So at this point, now that we've set up the problem, it's all really just about plugging in the numbers and adding things together. So make sure that you're using the correct specific heats. In this case, we're dealing with ice, the molar heat capacity, and the change in temperature. For the melting process, this involves taking the amount of substance and multiplying by the heat of fusion. Before you add together all of your heats, you're going to need to make sure that they have the same units. So we repeat this process. Anytime we have a temperature change, we use Q equals Cn or M times the change in temperature. Again, we use the heat capacity for the per upper phase, the amount of substance, and then the temperature change. Vaporization uses the amount of substance and the enthalpy of vaporization. Again, you would need to convert this into joules before adding together. Remember what we said earlier, that the melting process and the vaporization process require vastly different amounts of energy. We can see that that's the case here. It's almost 7 times more energy required to vaporize, versus to melt in the case of water. Then we finally have the final increase in temperature from 100 degrees Celsius to 130 degrees Celsius. To find the total heat, we simply add together all of the different amounts of energy. That then is the total amount of energy required to take solid ice, a mole of it, and convert to gaseous water at 130 degrees Celsius. All right, here's a problem for you to try. Pause the video and try to figure this one out on your own, and then come back and I'll walk you through it. Welcome back. So in this question, we have liquid nitrogen, and this time instead of putting it over some marshmallows, we are pouring it over some cucumber sticks, and that freezes them. We have 5 grams of cucumber we put in our mouth. We want to know how much heat will it absorb when it goes from negative 196 Celsius to 37 degrees Celsius. Again, from the boiling point of the nitrogen to our body temperature, assuming that cucumbers are 100% water. Well, so making the assumption that it's 100% water allows us to use the heat capacities of water, as well as the heats of fusion and vaporization of water. So the first thing that you should do here, again, we're recognizing here that the heat that is going to be absorbed by the cucumbers is the heat that's given off by our mouth. So if we wanted to ask how much heat was given off by the mouth, we would calculate initially the heat absorbed by the cucumber and then take the negative of that. So my recommendation is that you start by drawing a heating curve, that you label any relevant values in terms of the temperatures that you are aware of. We know that because we're going between negative 196 and 37, we're going to have to pass through the melting point of water. And so we want to include that on there. So we start as a solid. It increases in temperature up to the melting point, at which point we melt, and then we increase the temperature up to 37 degrees Celsius. We don't need to include the rest of the heating curve, which would involve going up to the boiling point, the vaporization process, and then also anything past that. So we have 3 calculations that we need to make here, one for each section of the heating curve. We have increasing the temperature from negative 196 to 0, the melting process, and then from 0 to 37 degrees. Anytime we have a temperature change, we're going to calculate that by multiplying the heat capacity times the amount of substance and the temperature change. The amount of substance we can find by taking the mass and dividing by the molar mass. Again, we've assumed that it's 100% water, therefore we're using the molar mass of water. We have then just over 1/4 moles of water. So to find the heat involved to increase the temperature initially, we multiply the molar heat capacity times the number of moles times the change in temperature. The melting process is going to use the heat of vapor or heat of fusion. So we take the number of moles times the heat of fusion to get about 1.7 kilojoules. To increase the temperature for the final leg of the reaction, we multiply the molar heat capacity for the liquid times the amount of liquid times the change in temperature. Converting that to common units, we get about 3/4 of a kilojoule. The total energy is found by adding together each of the steps, and we get just under 4.5 kilojoules. Again, if we wanted to determine the energy that was given off by your mouth, that would be equal to the negative energy that was absorbed by the cucumber. And so we would have the same value, but different signs. That's it for this video. Thanks for watching. Have a great day.